Hello everybody. I thought what I'd do, it might be a minor detail, but I want to make sure that we talk about it correctly. And that's the sign convention we use when we discuss simple harmonic motion. So let's assume that I've got a spring mass system and in this case the force is pointing this way as the string expands. And the mass gets further away, that force gets even stronger. We know this to be true because we have our old buddy Hooke's law. Which tells us that the more stretch you put on a spring, the larger the force. But keep in mind, this is still all happening in the positive direction. So if we do a quick little table, of force and x directions, whenever the force occupies the positive direction, we'll find the force pointing in the negative direction. When we swing around to the other side, so when we swing around to the other side of this, the x position is negative, while the force then has to point against the motion. We're going to get a force this way, because again you're stretching the spring, and the spring is going to increase the size of its force as you increase x. But we're increasing x in the negative direction, so that means the force is positive. Why do we care? We care because in the simplest of equations, where we'd have the force of the spring, I don't know why I put that line in there, and then we'd have the force normal and the force spring for our free body diagram. We're going to wind up with the force of the spring is going to equal mass and acceleration. And we also know that the force of gravity is going to equal the normal force in this case. But when we get back to the force of our spring, no matter where you put it in, it's going to come at us with a negative sign. Because if you plop it in the positive coordinates, you'll get a negative force. If you pop it into the negative coordinates, you'll get a positive force. This is better seen as negative kx m dx squared with respect to time squared. So this is why that force of the spring needs to be negative, is in order to add consistency between the two sides of the equation. Let's play the same game with a pendulum. So we'll put a ceiling up and we'll go this way or that way. I don't know why I'm putting X's. It's a pendulum, damn it. But theta positive is going in this direction. This would be theta negative going in this direction. And when we do that, the gravitational force, which would normally be straight down, the portion that is, so that's the force of gravity, and this way, and that has to be theta. The leg that is parallel to the moment arm we don't care about. So I can get rid of that leg. And what we're left with is that, let me make sure I'm actually, I didn't think I was, that we're left with the force of gravity equaling mg sine theta. Okay, so that means, again, if we do our little box, and we solved this using torque, and that'll be theta. So notice in this position the torque is negative, but the theta is positive. If we switch to the other side, that'll be our force of gravity in the important part is that we take the length and the force, and we find the torque is now pointing up and is positive, but theta is in the negative direction. So this is why when we calculate our torque, sum of the torques is equal to I alpha. We get the torque, mg, make this a length L, sine theta equals I alpha. When we're in the positive theta direction, so when theta is positive, this overall torque then needs to be negative. So that's why we have the positives and negative signs in front of these equations, which make them possible for us to solve.